Today we'll talk a little about the inverse matrix and some matrix algebra. So the concept of an inverse, first of all, if we think about the inverse of a real number, it's really the reciprocal of that number. So 2, in this case, raised to the -1 power equals 1/2. So what does that mean? Well, the reason the inverse is important because if we multiply the inverse by the non-inverted value, we get 1. So 2 times 2 inverse, which is really 2 times 1/2 equals 1, and vice versa. 2 inverse times 2 is equal to 1. So for a matrix, the idea is pretty much the same. A times the inverse of A is equal to the identity because I, or the identity matrix, is the matrix that's equivalent to 1. So when we multiply something by the identity, we don't change it. Similarly, we would expect that the inverse of A times A itself would equal the identity, regardless in which order we multiply the inverse in. Okay, so the tricky part here is that the matrix of an inverse is not simply found by taking the inverse of the values within the matrix. We know things are a little bit more complicated with anything that involves matrix multiplication. So if you try to take the inverse of each of the individual elements and multiply the matrix A by it, you're not going to get the identity. So then how do we find it? Well, think in terms of matrix arithmetic. So let's start with a simple case. If we put the number we wish to invert on the left side of an augmented matrix and 1 on the right, then whatever operation we perform on that row gets recorded on the right. So remember that when we use reduced row echelon form or Gaussian elimination, we often place the coefficients over here and the constant here. But let's think about it this way. If I put the number I want to invert on the left and then the identity on the right, and now I do any row operation on just that one row, for example, in this case, to make the value 4 to find the factor that cancels it out and turns it into a 1, well, I know that I have to take 1/4 times that row, and I do that. So I take 1/4 of 4, I get 1, so I've already inverted 4, and then over here, this 1 records everything I've done. So I've multiplied that entire row by 1/4, which means I've scaled 1 by 1/4, and so now whatever value, now once I get the identity on this side, whatever value or values I have over here represent the inverse. So 1/4 is the inverse, and we know that. So that's how it would work in a very simple case. We would do the same thing for a matrix and its inverse, except put 1 or I in the augmented portion. So in this case, I'm going to have my matrix A, let's say it's 1, 2, 3, 4, and I'm going to have the identity over here, and then I'm going to perform Gaussian elimination until I get the identity over here, basically until I've effectively canceled out the matrix, and everything that I've done gets recorded on the right. So we perform Gaussian elimination, and now we see that this becomes 1, 0, 0, 1, and that and it's the standard Gaussian elimination, same as we always would, except we have 2 columns that gets changed simultaneously over here, and we would get this element. So we're arguing that because everything gets recorded in the identity, and once we have the identity here, i.e. we've canceled out matrix A, this should be our inverse. So we claim that A inverse equals this matrix. Again, note that it's not simply the inverse of each of the matrix values. So how do we check? Well, if we take A times what we claim to be A inverse, we indeed get 1, 0, 0, 1. If we take A inverse times A, we again will get 1, 0, 0, 1, and therefore we know A inverse is the identity matrix. Excuse me, A inverse is in fact found correctly. Now we would do the same principle for a 3x3, except back here where we put the 2x2 matrix, we put a 3x3, and over here where we have the 2x2 identity, we put the 3x3 identity, and we do reduced row echelon form, get it into reduced row echelon form, and we would get the same result. The only constraint here is that this only works for square matrices. They only have inverses, and to think about why intuitively, it's because the identity matrix is always square. So the only matrix that you can multiply something by and not change it is the square identity matrix. I shouldn't even have to say square identity. The identity matrix is always square. So it has the same number of rows as it does columns. So what can we do with the inverse? Well, let's say we want to solve a matrix equation that we set up, and we'll see this a lot later on. AX plus B equals C, where A, B, and C are some matrices that contain constants, and X contains variables. So we're assuming X is square. And then in that case, what we can do is we can subtract a matrix from both sides. So subtract B from the left, subtract it from the right. Matrix addition is commutative, so I could have written -B plus C. but the negative is attached to the b. And now what I'll do is I'll multiply both sides by the inverse. So I'll multiply by a inverse. Notice how I'm multiplying it on the left. So I have to multiply it on the left here as well. And I technically could distribute, do a left distribute, make this a inverse c minus a inverse b. But once I multiply a inverse times a, I get the identity times x equals a inverse times quantity c minus b. And we know that the identity multiplied by any matrix is simply that matrix. And therefore, I've effectively algebraically solved for x. And now, if I know what's inside of a, b, and c, I can go to my calculator computing system and simply calculate a inverse c minus b. So again, just notice that we multiplied by a inverse on the left-hand side, so we have to multiply on the left on the right-hand side. That's very, very important. If this were x times a, then I would have to have multiplied it by a inverse on the right, and I would have had to multiply by a inverse on the right over here as well. That just emphasizes that matrix multiplication is not commutative. In general, AB is not equal to BA. So let's say we want to use this to solve a system with two variables and two equations. So here are my two equations. Now what I can do is I can form a coefficient equation, 3, 2, 1, negative 1, times or I'll just call this the matrix, the variable matrix, xy, equals the constant matrix A2. Now this works out because if you notice what we've really done is we've kind of extracted the xy vector because we have a sum of products, and we see that we have a 1 and a 1 here, a 1 and a negative 1. So we've kind of lifted up the xy vector. Now if we were to multiply it back in, we'd see we'd have x times the 3, 1 vector plus y times the 2, negative 1 vector, which is really just this expression over here. And all I've done on the right is just turn that into a matrix. So I have something of the form ax equals b. And what I can do is multiply both sides by a inverse on the left, and I would get x equals a inverse b. So in a calculator, normally we don't really care what's inside of a inverse. We just care that a inverse can be found. So I go over to my calculator, I type in the matrix. Most of the time you can just do caret -1 power. Some computer systems actually have an inverse button. And when I multiply it out, I get 2.40.4. And I can just verify from the second constraint that the difference between these is exactly 2. So it appears that it works. When does A inverse not exist? Well, it doesn't exist when there are infinitely many solutions, or when there are no solutions at all. So if you think about it, back here, we get exactly one inverse. And because we get only one inverse, the product between that inverse and any other matrix will produce a unique matrix. It's not like when I multiply these today, I'll get 2.40.4, but when I multiply them tomorrow, I'll get some other two values in this matrix. We're always going to get the same answer. So the only cases where they don't work is when there are infinitely many or when there are no solutions. And all of these two cases are equivalent to the following. If A inverse does not exist, that's identical to saying that the columns of A are linearly dependent. Think about what happens when we have linearly dependent columns. We get certain rows that cancel out completely, and therefore we couldn't possibly reduce it down to the identity. And we noticed this was the case. You could not get the identity matrix whenever you had linearly dependent columns. Similarly, it doesn't exist when A is not square. So that's not really equivalent to these cases because sometimes you could have linearly dependent columns in a matrix and the matrix still is square, but this is another case where A inverse doesn't exist. And when the determinant of A is 0. So what's the determinant? Well, that's one thing that we'll talk briefly about here. The determinant helps me really determine the nature of a matrix A, okay, or whatever the matrix is called. So we'll write det A, or you can put A in these straight brackets, or you can put the matrix values inside these straight braces on either side. Okay, well, this is a measure of linear independence in a way. And it's just a value that you get when you calculate the determinant of A, and it tells you everything you need to know about invertibility. So consider the general matrix A, B, C, D. Suppose I want to find the inverse of A. So what I do is I set up the matrix I want to invert on the left, the identity on the right. I perform Gaussian elimination. Now, if I did this in a computer system that allows me to take inverses with symbolic quantities, here's what I would get. So it looks kind of intimidating at first. But the one thing that we should point out is that there is a slight potential problem in this being the inverse of the matrix containing the values a, b, c, d. We have a denominator, and all of these denominators, notice, consist of the product the difference of the two products AD and BC. So if AD minus BC, if this denominator is ever equal to 0, then clearly an inverse isn't going to exist, because of course we can't divide by 0. So it makes sense that in that case this could not be an inverse. So the inverse will exist as long as that denominator is not equal to 0. And guess what? That's what we say to be the determinant of A. This quantity, this denominator, determines whether an inverse will exist, and it will only exist if AD minus BC is not equal to 0. So we can also write that the determinant of ABCD is AD minus BC. Now, to give you kind of a visual of this geometry, it's kind of cool. AD is the product of the diagonals from top left to bottom right. BC is the product of the diagonals from AD minus BC, is the product of those minus the product of those. Okay, so another way to think about it more intuitively is, suppose we have two linear functions, ax plus by equals g, and cx plus dy equals h. So a, b, c, d, g, and h are all just real values. Well, we know there will be exactly one solution only if the slopes are different. Otherwise, there are no solutions, or infinitely, I should say many. So if the slopes are different, we will ensure there will always be exactly one solution. It might be in the first, it might be in the second, it might be in the third or the fourth quadrant, but there will be exactly one solution. So let me set these up. Let me solve for y here. If I solve for y, I get negative a over bx plus g over b. That's from solving this one for y. And in the second one, I get y equals negative c over dx plus h over d. Well, I want the slopes to be different in order for there to be exactly one solution, so I can set up an equality or a non-equality. Negative a over b cannot be equal to negative c over d. The slopes can't be the same if I want exactly one solution. Well, that translates to, if I do a little bit of algebra on this, multiply both sides by b, I get negative AD. Multiply both sides by b, I get negative BC. And those two things can't equal each other. Well, if I divide through by a negative, I get AD can't equal BC. And if I subtract BC away from both sides, I get AD minus BC can't equal 0. Well, hey, guess what? There's the determinant again. That's just another slightly more intuitive way to think about it, setting the slopes equal to each other, or in this case, putting in a not equal sign between them. So what about larger square matrices? Well, they're trickier to compute in general, but it's the same idea. You can do it with a calculator, you can do it in a computer. It's very simple to do, but there's no sense to me in actually doing the computation because it gets tedious, but it's kind of the same idea. Except in 3 dimensions, you have multiple slopes. You have a slope in the x direction and a slope in the y direction that needs to be checked. So in general, if A is a square matrix, then we say A is invertible as long as the determinant of A is not equal to 0. Okay, so that means an inverse exists. That means there's only one solution. That means the slopes are not equal to each other. And we say that A is non-singular. That's just the label we give it if A is invertible. If A is not invertible, in other words, if the determinant of A equals 0, so if the slopes are the same, then the determinant of A equals 0, and A is called singular in that case. These are kind of hard words to remember, but it seems like it should be the opposite way around, but it's not. The determinant will become very useful later on. We'll actually use it a great deal in applications, such as when we're working with eigenvalues and eigenvectors. It's an invaluable concept. It does more than just tell us about invertibility. It allows us to actually set up meaningful equations. So that's it. Hopefully this has been helpful, and that's just kind of a brief introduction to the idea of finding inverses and computing determinants.